I was, I don't like it when my students are all here at the very end, and most of y'all were still here, but y'all actually did pretty well. Because usually if the students are here, that means that the class didn't do very well as a whole. So I like for the first students to start leaving it about 25 minutes before, or 20 minutes. But I was glad, like, as a class, y'all did pretty well, actually, better than I thought. But I want to show you something. Online, there's a grade calculator. Well, there's not, but I will put one on there. It's on the other class. Let me pull it down. And this just allows, it's just a spreadsheet. I mean, you can do this on your own. It's just calculating the averages. But I just want to give you a feel for sort of how this class is laid out and what grades mean, a grade on a particular exam. Let me blow this up so you can see it. Oh, goodness. That's too big. All right, so these are your grades. You have 4 exams, a final, class participation, and then in the next week or so, I'm also going to send out an email, a notice about extra credit. You will be allowed to get 20 points of extra credit, and that's just sort of thrown into the pot. It won't be terribly complicated. I guess not like a big paper you have to write or whatever. It's just a few little things that you'll need to do. It'll be online on Moodle, and I'll send out a notice about it. So these are all the maximum grades that you can get on things, and then here are some sample grades. So let me just show you some scenarios that you might encounter. Like, let's say that you just really bombed this exam and you made a 50 on it, all right? And then what do you need now to get a C in the class? Well, really, to get a C in the class, you just really need to get 70% on all the finals. I mean, on all the exams, 70% on the final. The final's worth 150, so that'd be 105 points. Your class participation, which I fully expect everybody to get the class participation, you just need to come to class. In reality, there are going to be a few people that won't get that full amount because they didn't come to class. But if you come to class regularly, you'll get that. And then the 20 points. So that student will have a 73. So actually, they can make like a 67, 68% from here on out, even though they made a 50 on the first test and still pull a C. All right, and in fact, this person can probably still get an A, like if they do well on all the other exams, say 95%, yeah, they can still get an A, probably about a 93%, 92%, and still pull an A in the class. So even if you just bombed this exam and made a 40 or even less, you can still do well in the class. And if you made an A or a B or even a C, then you're tracking along pretty well. So my point is that there's just a lot of points to be had in the class, and so one single exam, it only counts about 15% of your total grade. I think that's right, isn't it? Let's see, 100 divided by 600. Yeah, 16% of your total grade. All right? So if you made a, yeah, so 16%. And that extra credit, by the way, it seems like a lot, 20 points, but it's not really. It's about 3 percentage points overall. So I recommend that you do it because you never know if that 3 points is going to help you. But I know statistically, like if you look at the class, it's only going to help about a third of you, right? 3 points will pull up about a third of you, a letter grade. But, you know, if you're in that third, it's a good place to be, right? So I'll send that out, that extra credit the next week or two. It won't be complicated, just I'm not sure what right now. You have any questions about the exam? I will post the solutions sometime today or over the weekend. I have them, I just need to put them on YouTube. And I'm going to hand the test back today. All right? It was a pretty good first exam. I know some of you aren't pleased with it, but it was a pretty good first exam. It was, I don't think it was terribly easy, right? Not too easy? Okay. But, you know, it's not an easy class, but this is probably one of your first difficult classes that you'll have in college, right? Is it your first difficult class? Huh? Yeah. Okay. Good. All right. And now we're going to move on to Chapter 3. In Chapter 3, we're going to see some of the same stuff. Today we're going to look at vectors, and that might flow over into Monday as well. And then we're going to spend time on projectile motion. So that's going to be a lot of what we've done already, in kinematics when we're dealing with projectile motion, except with projectile motion, instead of having just motion in one dimension as we've been having, we'll now have motion in 2 dimensions. And so it'll be a lot of what we've been doing, except we're going to expand it into 2 dimensions. You'll also have some questions on the next exam just about vectors, adding and subtracting vectors, and let's see, most of you are in Thursday's lab, right? Yeah, so if you're in the lab, you've already done this lab on vectors, where y'all did the scavenger hunt. Have y'all done that yet? Yeah. So we'll do a lot of that same stuff. What's this? The next exam will likely, for y'all, cover chapters 3 and 4, maybe. What page are we on here? 76, thank you. Alright, first I want to watch a little clip. This is from Bob the Builder. Y'all ever watch Bob the Builder? Bob the Builder. I got a little boy, my little girl liked Bob the Builder too, but we spent probably too long watching Bob the Builder. This has Spud in it. Spud is like the Scarecrow character in Bob the Builder. I personally think he's a little sketchy. Spud, you might know Bob the Builder. Spud, I think he's a little sketchy, but you can let me know what you think. And they're talking about how to get from one point to another. You can take a long circuitous path, or you can go, as Spud says, or as Farmer Pickles says, who's a very level-headed character, you can go as the bird flies, or as the crow flies. So it sort of fits in with what we're doing with vectors. I can find the darn thing. There it is. So the point is here that when we're talking about vectors, that we can really think about them as displacement vectors. I think are a much better way to think about vectors and how we add vectors. So let's say that we want to get from one point to another. We can take a route that takes several vectors, like this, and following those displacement vectors will get you from your initial to your final position. Or we can take a similar route that will get us from this point to this point. Now, if these vectors are A, B, C, D, and E, the sum of all of these vectors is going to be the same as this vector. So this will be the sum A plus B plus C plus D plus E. All right, and this is the graphical method of adding up vectors. And I think it makes intuitive sense when you look at it in terms of displacement, that these two sets of vectors are the same because they have the same initial and the same final position. Remember, that's how we define displacement, as the final minus the initial position. Remember, vectors have magnitude and direction. And scalar quantities have only magnitude. Remember, we talked about in chapter 1, what are some vectors and what are some scalars. Vectors include some of the stuff we've already done: acceleration, velocity, displacement, things that we'll do in the coming chapters: force, work, current will be a vector, or not current, but we'll talk about current later. And anyway, there are a lot of different vectors, and then there are also scalar quantities like time, length, mass, charge. So a lot of different scalar quantities as well. We usually draw vectors with an arrow. So that is, when I write a variable that's a vector, say velocity, I should write it with an arrow over the top. I don't always do this. Often when we're working in kinematics problems, we don't do that because we're just talking about the magnitude of that vector. But we should draw them with an arrow over the top. F, for example, A, for example. And when we draw a vector graphically, we'll draw it like this. And y'all did this in the lab, where you draw it as an arrow. And here the length of the arrow gives the magnitude. While the direction of the vector is just the direction the arrow is pointing. Alright, so for example here, if this is a displacement vector, right, this length, whatever the length is, will represent the magnitude of that displacement vector. And then we can also describe the direction based on this angle theta. So whenever we talk about vector quantities, we'll give both a magnitude and a direction. And usually it's some value for the magnitude, and then some angle that's measured in respect to some axis. Y'all did this in the lab. So for example, if I have two vectors, say I have a vector that looks like this, and then a vector that looks like this. The smaller vector has the same direction, but as I've drawn it, it has 1/2 the magnitude of the larger one. All right, because I've drawn it half the length of the first vector. That's just how we represent vectors. We represent them as arrows. The length of them gives the magnitude, and then the angle gives the direction. We can also take vectors and move them around. So for example, say we set up our coordinate system like this. This is our x coordinate, this is our y coordinate, and then we draw vectors. We draw a vector here. So that's some vector, I don't know, let's call it r. All right, that vector r is the same if I draw it over here. It's the same if I draw it over here. It's the same if I draw it over there. As long as I keep the same magnitude and direction, I can move that vector around however I want. It's basically you're moving your coordinate system, and I can move my coordinate system however I want. Okay, so I can move these vectors around as long as I keep their same magnitude and direction. So as long as you don't change their magnitude or their direction. And so that gives rise to the geometric method of adding vectors. This has a lot of different names. I think in the lab you might have called it the graphical method. Also, you might have called it, your lab manual calls it the polygon method. The geometric method, or sometimes it's also called the triangular method or the tail to tip. Those all refer to the same thing. And in short, it just means that you have two vectors. You can put them tail to tip to one another, and it creates like a triangle, so hence the triangular method. And when you connect the tail of one to the tip of the other, that will give you the resultant vector. Let me show you. So let's say that I have a vector A that looks like this, and then I have a vector B that looks like this. You can draw it like this, but I'm going to show you something. So I have a vector A like that, and then my vector B is over here somewhere. I can take that vector B. Remember, I can move a vector around however I want, as long as I keep the same magnitude and direction. So I can take this vector B and translate it over here. And so if I move that vector B over here, that's my vector B. Then I can connect the tail of A to the tip of B, and I get the vector A plus B. And again, if you forget how to do the graphical method, just think back to our displacement vectors. As long as I start at the first point and end at the final point, no matter if I go this way or if I go this way, these two vectors are going to be the same. But I always start at the beginning, that is the first vector that's listed, and then I end at the second vector that's listed, A plus B. You might have a simple question. Likely you'll have multiple choice, but you might have also a graphical component to a vector addition problem, kind of like you did in class, where I won't make you use a protractor and a ruler, but where you have to sketch out some vectors that you've already found numerically, that you've already added up numerically. I'll show you some examples in just a bit. So you can find the sum of the vectors by placing them tail to tip, as we've done here. And then connecting the tail of A to the tip of B, like in this figure. You can also take the differences. Oh, let me show you something else, actually. You can also, instead of drawing A plus B, you can draw B plus A. And in vectors, when you're taking the vector sums, A plus B is equal to B plus A. Does anybody know what this is called? The commutative? That's right, yeah, the commutative property. Y'all will do this in Calc 3. I think, anybody in Calc 3 right now? No, but you'll do this. Y'all have, as chem majors, you have to take Calc 3. I think the engineering majors have to take Calc 3 as well. Yeah, so you'll do a lot of vector stuff. So all this stuff will come back. You'll do cross products, dot products, all that jazz in Calc 3. And probably some vector addition as well. All right, so this is the commutative property. And what that means graphically is, you know, A plus B looks like we've already drawn like this. So this is A plus B. B plus A, on the other hand, you just draw them in a different order. This is B. This is A. Sorry, it's a little wiggly. But this is B plus A. Alright, but notice that A plus B and B plus A, these two vectors are exactly the same. And that's called the commutative property. I'm going to write it down. You don't need to know it for this class, but you might see it again in other classes. That holds for vectors. It holds for other things too, right? Just digits, right? 1 plus 3 equals 3 plus 1. But it also holds for vectors, the commutative property. You can also take the differences of vectors. So if you are subtracting vectors, you simply switch the direction of the vector that's negative. So, for example, if this is the vector B, the vector negative B looks like that. And so whenever I'm subtracting two vectors, say I'm taking the difference A minus B, I'm just going to switch the direction of B. So let's say that I have a vector A. We'll use the same ones we did before. This is the vector A. This is the vector B. And then if I want to take the difference in those, I will, I'm going to do it here in the middle. I'll do first A. There's my vector A. And then I'll draw the opposite direction for B. So this will be negative B. See, I just switched the direction of B. And then the vector that's the sum of those will start at the beginning of A and end at the end of B. And so that's going to be A minus B. All right, so we can take a negative of vectors. You can also do it for more than two vectors. And that's, so right here we would call this the triangular method. But if you do it for more than two vectors, you don't make a triangle anymore. You make a what? A polygon, right? So that's why they call it the polygon method, more general. Those of you who are going into engineering, you'll spend a lot of time on this in statics, I think. You spend a lot of time just adding up vectors because it's important for doing force diagrams. When you have a lot of different forces that are involved, you have to deal with a lot of different vectors. Y'all take statics and geomatics? No. They used to take it for applied science, but they don't have that program anymore. So if you have more than two vectors, it'll look like this. A vector like that, vector like that, like we did for Farmer Pickles and Spud. The sum of the blue vectors will equal to the red vector. And so that's called the polygon method. But it's the same as the triangular method. It's the same as tail to tip. They're all the same. But they just have different names. All right. Let's take a couple little questions. We'll see several questions. And again, you'll see these again on the multiple choice part of the test. Y'all did really well, actually, I thought, on the free response. I was really proud of y'all for just doing well in the free response, but a number of you missed questions in the multiple choice, and so that sort of hurt some of you, that you just missed those multiple choice questions. I don't know why. I want that to be an easy 30 points for y'all. The way you prepare for those, study through the concept test, and then just sort of look back at the general knowledge on your notes. So like, for example, on this previous test, that would be like the standards and, I don't know, the dimensional analysis, that sort of thing. Right. So I want that to be an easy, well, not easy, but I want that to be a 30 points that you can pretty much count on. All right, so let's say that we have vectors A and B, and they have magnitudes 12 and 8. If I add up these vectors A and B, what are their maximum and minimum values? Now what I've drawn here, first of all, is that this symbol right here represents the magnitude of A. So anytime I draw a vector and then I put absolute value bars around it, that just means the magnitude. So it has a magnitude of 12 at some angle, I don't know what that is. And this B has a magnitude of 8. What is the maximum value if I add up those vectors? What's the maximum value I can get? 20, right. So if they're both in the same direction, I get a maximum value of 20. So if A and B look like this is 12, this is 8. If I add those up, it gives me a magnitude of 20 units. What is the minimum value then? 4, right. So if they're opposing one another, if one is in this direction and one is in this direction, then the sum of those two vectors is going to be 4 units. All right, now the range then can go anywhere from 4 to 20, because these vectors can also be at an angle to one another. But if they're at an angle to one another, the sum of the two vectors will never be less than 4 and never greater than 20. It'll be something in between. So that's the limits of those vectors. We'll see some questions like that in a bit. Let's see, let's try this clicker question. I have two vectors, A and B, and I want to know what is the difference A minus B. All right, I don't know if you can see the letters here, but this is option A, this is option B, this is option C, and that's D. So what is the difference A minus B? So remember, if you have a negative vector, you just switch the direction. Courtney, you don't have your clicker today? Okay. Anybody else missing theirs today? I don't know how many people we had. All right, just a few more seconds. I'll stop it. Say 1. Yeah, I think that's everybody. Okay, we're sort of all over the board, but D is the right answer. All right, so to do this, we first draw the vector A, like this, and then we draw the vector negative B. So negative B will look like that. And then we connect here from the beginning to the end. And so that's going to be our difference, which is D. That is what I marked correctly, isn't it? D? Yeah, that's very good. You will see a question like this in the multiple choice part of the exam. But as I said, I might also give you a question in the free response where you have to add up vectors numerically, which we'll do in a bit, or probably next time, and you did in lab. And then I might also have you sketch out those vectors and do it graphically as well. Well, let's try this. Right, I'll stop at about 110. 10 more seconds. It's 5 seconds. Alright, C is the right answer. Just like we did before, this goes as a range from 25 minus 12, that's 13, is the lowest value it can have, to 25 plus 12, which is 37. So somewhere between 13 and 37, and the only one that falls there is C, 32. So that's the only one of these that could possibly be the sum of these two vectors. All right, one more thing, and then we'll do some concept test questions, is the components of a vector. I just want to show you that you can have components of a vector. Components are like a projection of the vector onto the axis. I always like to think of like a flashlight shining down on the vector. So if I shine a flashlight from here onto the vector, it will project a shadow of that vector onto the y-axis, and that's going to be our y component. So it's just a projection of the vector onto the y-axis. You can find it just when you graph it, if you just drop a horizontal line over to the vector, and it'll give you from the beginning point of that vector A up to where you drop that horizontal line over, it'll give you the y component. So this is just a projection of the vector onto the y-axis or onto the x-axis. Now I can also redraw this, because remember, I can take my vectors and I can move them around however I wish. So I can take this vector and move it over here. If I do that, can redraw my AY vector. Alright, and if you see this, it should stand out to you. Right here I have this triangle, and if I have AX and AY situated in this way, AX like this and AY like this, if I add those two vectors up, AX and AY, what vector will they give me? They'll give me A, right? So that's our triangular method. So the sum of our components adds up to give the original vector. So that is that AX plus AY will equal to A. The vector sum of AX and AY will equal A. Now again, this is the vector sum. So if AX has a magnitude of 3 and AY has a magnitude of 4, that doesn't mean that A is going to have a magnitude of 7, right? And in fact, A will have what magnitude if AX is 3 and AY is 4? It'll have 5, right? So it's our vector sum. It's going to require Pythagorean theorem and our trig functions and messing around with right triangles. And we'll do that in just a bit. But right now I want to just do some general questions for the concept test. So get your clickers out again, and we will do some of these. For chapter 3, we won't do them all. Just do a handful of them. Y'all study the concept test for the test? Yeah. Good practice is to print them out and then to fold them and print 6 slides to a page and then fold them in half, and you can quiz yourself on them. Alright, two vectors are given such that A plus B equals 0. What can you say about the magnitude of the vectors A and B? So when I write it like this, simple with 2 arrows and PowerPoint, this means the vector sum of A plus B. So the vector sum of A plus B equals 0. What can you say about the magnitude and direction of vectors A and B? Just a few more seconds. 45. Very good. They have to be in the opposite direction. They have to have the same magnitude, and they have to be opposing one another in order to have 0 magnitude. Alright, vector sum A plus B equals C. And then it can also be said that the magnitude of A squared plus the magnitude of B squared equals the magnitude of C squared. How are they oriented with respect to each other? Remember, these also are in the back if you want to mark your answers in the back as well. Stop at 55. Just guess if you don't know. Okay, very good. Why is it that they're perpendicular to one another? Right, but what is it about that a squared plus b squared plus c squared? What is that? Okay, it's only for right triangles. That's the Pythagorean theorem. All right, given that a plus b equals c, that is the vector sum, a plus b equals c, and then also the sum of their magnitudes, a plus b plus c equals c, how are they oriented with respect to each other? So the vector sum, a plus b equals c, the sum of their magnitudes, a plus b, also equals c. So how are they oriented? What orientation of vectors will make both of those statements true? Just a few more seconds. Okay, parallel and in the same direction. So this is saying that if I add these two vectors, a and b, they give the vector sum c. But it's also saying that if the magnitude of a is 2 and the magnitude of b is 3, then the magnitude of c has to be 5. And that's only true if they're parallel and in the same direction. Very good. Y'all doing pretty good on these. All right, if each component of a vector is doubled, what happens to the angle of that vector? So we describe vectors with an angle, theta. What happens to that angle if I double both components? Think back to high school geometry. Just a few more seconds. 43. C is correct. Good. It does not change. What types of triangles are those called? Do y'all remember? It starts with an S. Similar triangles, right? So if I have two triangles, was that somebody or is that something else? Was it seriously that? The no smoking sign? I asked my wife, we were on a plane over the summer, I was like, you think they'll ever turn off that no smoking sign? I was like, I really want to light up. I don't smoke, but so if I just double them, these are called similar triangles, and this angle is the same if I increase each side by the same amount. I used to smoke a bunch of years ago. It's very bad for you. I know some of you probably smoke. You should quit. Like, it's really bad for you. What's that? Or do you smoke? No. Okay, a certain vector has x and y components that are equal in magnitude. Which of the following is a possible angle for this vector? Alright, so a few more seconds, I'll stop at 50. 50. Okay, E is the right answer. If my vectors have components that are equal in magnitude, so I have an x component and then a y component, then this angle, this is an equilateral right triangle, that angle has to be 45. It's an equilateral right triangle which has 45, 45, and 90. It's not the only angle, right? What are the other angles that can give equal magnitudes for the x and y components? 135. That is measured from here, 135, and then let's see, 180, what's that, 225? You get the idea. So it can be in all four quadrants. So, for example, our x and y components, say for this vector, it would have a negative x component and a negative y component. And in the second quadrant, which vector would be negative, the x or the y? The x would be negative, and in the fourth quadrant, the y would be negative. All right, so when we're dealing with vectors, we have to be very careful about how we describe the direction, and you'll see this in some of the problems that we'll do, that we'll always describe the direction as being from the positive x-axis, but sometimes we won't describe it. We'll actually describe it from being the negative x-axis or the positive y-axis. We'll see that when it comes up. Okay, just a couple more of these. You're adding vectors of length 20 and 40 units. What's the possible resultant magnitude? Seen a similar question already to this. Just a few more seconds. I'll stop at 40. C is right. We had that already. It's between 20 and 60, right? So if they're in the same direction at 60, if they're in opposite directions, the minimum is 20. Okay, and we'll come back to this. The second part of chapter 3 is on projectile motion. We'll come back to this later. Let's see what else we have here. Want to go and define how we find our x and y components? You should know this, and we've already been over the review of trig, but just to remind you, if we have a right triangle, I have a side here, this is my x component, and this is my y component. I can figure out the magnitudes of those if I know the magnitude of A, and I know the angle theta. Now remember our SOHCAHTOA. Alright, so if I take the sine of an angle, theta, that's equal to the opposite over the hypotenuse. And so as I have it drawn here, it's going to be AY over A. And then the cosine of the angle theta is going to be what over what? AX over A, right? So that's the adjacent side over the hypotenuse. And then so from that, I can get these expressions for AX, if I cross multiply, is equal to A cosine theta, and AY, if I cross multiply, is equal to A sine theta. So that's where that comes from. Those are our expressions for our x and y components. Now, if we change the angle, where we measure the angle from, say I'm measuring my angle up here instead, say I call this the angle phi, then it changes how we calculate our y component and our x component. Our y component would be A times what? In terms of the angle phi. What would it be? Right, the cosine phi. And then because you see now, the y component here is the adjacent side to the angle. And then my x component would be what? A sine phi. Not theta, but phi. right, or phi as I'll call it, but phi. All right. So be careful when you're finding the x and y components of a vector, because it's really dependent upon where your angle is measured from. Now, usually it's the case that your angle will be measured from the x-axis, almost always, but it's just on some occasions where that angle is not measured. I always like to remember that my x and y components, because I can't go through this whole cosine is adjacent over hypotenuse, all that jazz. Every time you work a problem, it's always useful just sort of to know this. I remember it because it's alphabetical, right? X and y, cosine and sine, cs, xy, those are both alphabetical. So this is sort of the normal way for doing our components of vectors when our angle is measured from the positive x-axis. And if you ever encounter a time when it's not measured from the positive x-axis, you can always just do a quick 90 minus whatever that is. So let's say that you know that this is 30 degrees, and you know this angle has to be what? 60. In chapter 4, we'll encounter some places where our angles are measured from a different axis when we're doing inclined planes, and you'll see how that will come useful for you. But I always just like to remember that this is true most of the time when our angle is measured from the x-axis. We can also, if we have the x and y components, we can use our tangent function, as we've already done in chapter 1, to find that angle, an unknown angle. And we'll do that next time when we'll do several examples of adding vectors. Let me just cover this right quick. This really only comes up in chapter 4, but in some cases you might need to rotate the coordinate system. And then I'll hand back your exam in just a second. All right, so say, for example, I have two vectors like this, and to draw a coordinate system like here, like I normally would make the problem fairly difficult if I were trying to add up those vectors. And so it's sometimes a lot easier to rotate the coordinate system so that now this would become my y-axis, and see the vector is on the y-axis, and this would become my x-axis. So now you have these two vectors here. This would assume that theta would equal phi, so these are the same angles. You have these two vectors that are now on the x and y axis. So the point here is that you can do anything you want to with your coordinate system, and again in chapter 4 we'll see where this becomes useful. So don't worry too much about this right now. We'll deal with it later. Don't worry about this. This will come back a little bit later. All right. We're going to stop there, but next time we're going to work some problems where we're adding vectors. Very likely to have a problem on your exam, a free response problem, 10 or 15 points. So you have to add up some vectors. But then, of course, we're going to be adding vectors a lot in the upcoming chapters, next 3 or 4 chapters. We have a lot of vector addition. All right, I'm going to hand back your exam. Just want to give you a quick primer on what the numbers mean, because